Hello, this is Clint Halstead, and I'm going to do a lecture on Chapter 1 of Designing Embedded Systems with PIC Microcontrollers by Tim Wilmshurst. Okay, so this is the second edition of Tim Wilmshurst's book. Okay, hopefully you have the book by now. So the first question that we're going to ask in this chapter is, what is an embedded system? And the second objective is to figure out, what types of embedded systems do you know? Okay, in this video lecture, I'm going to cover sections 1.1, 1.2, and 1.3, and then I'll cover 1.4 through 1.6 in the next half of the video series. So, if you look at a refrigerator the modern refrigerator has many times digital buttons that need to be pushed and indicators, temperature control. Even the refrigerators that you don't see a lot of buttons on, they're going to have a lot of control. It's going to have a microprocessor embedded inside of it. And what the processor does is it basically takes the required temperature reading. It takes it has inputs. So this represents inputs. On the bottom here, required temperature, actual temperature. Now this arrow represents some outputs: the display, the alarm, the compressor control. So if the temperature is not the current temperature sensor says that it's not at the temperature setting, which has been set by a keypad or something like that. If it's not at the right temperature, then it needs to turn on the compressor. And then the microprocessor will sample that signal until the temperature reaches the value that's needed, and then the microprocessor will shut off the compressor. So you have the inputs and you have outputs, and you have some human interaction as well. So human interaction would come in on keypads or buttons that go up and down, possibly even network. So this is an example of an embedded system with a microcontroller. So an embedded system, according to the textbook, is a system whose principal function is not computational, but which is to control by a computer. Okay. Some other examples of this would be possibly a car, a two-door car, where you have a window motor, you have a lock control, you have an actuator, you have a window stall sensor, open door sensor. Okay, so the inputs to the microcontroller would be the lock control, okay, the buttons, and then the output would be a motor that controls the window. So you could have your microprocessor do all those functions. And you could even have, the microprocessor could do multiple different things. It could be a computer under the seat or under the hood that would have inputs, the buttons that you typically have, the window, up, down, the mirror. Many different features in a car, and so that's an example of an embedded system. Many times in an embedded system you don't really know that there's a computer in it. It doesn't really look like there's a computer or a microprocessor in it, but in fact there is. And that's why we call it embedded, because it's embedded down deep inside of it, and you may not even know that it's there. Whereas a traditional PC or computer, obviously that you got a computer, then you have a microprocessor inside of it. So almost everything these days has, almost all electronic devices, your gas station, your washing machine, your fridge, burglar alarm, microwave, toys, photocopier, checkout machine, printer, scanner, brakes, engine control, all of that stuff has a embedded microcontroller inside of it. And once you do have the microcontroller in place, it's basically a little tiny computer, then there's tremendous opportunity for added value. You can do many things that you never thought you could use before. Okay, so the idea with the microcontroller would be you want it to be small, cheap, and efficient. So in this case, it's not a huge computational power. An example in this book that they talk a lot about was the Durbot autonomous guided vehicle. We're not actually going to design this in the class. We're going to use a PIC lab kit, and we're going to do several different labs and interesting projects. But this project in particular, we're not going to handle in this class. This would be more like an advanced or a second year project class. So since this is just an introduction class, we're not going to be doing this project. But it would be a good project to do. And you can see it basically has a keypad for input. and then LCD panel. And we will try to use the keypads and LCD panels. I do plan to do those, so you're going to get your hands dirty with that. We're just not going to be doing something quite this complicated. But you can see in this system that you have some inputs. You have a bump sensor, a light sensor. Those are inputs, a bump sensor right, light sensor, and then you have an output, which is a servo sound. And then you have a motor driver output, and then you have a range sounding module. And then of course you have power and regulation. So you're always going to see these. There's always going to be a need for some inputs typically, and always outputs. So look in the direction of the arrows. Will tell you if it's going into the chip, if it's going into the microprocessor, that's an input to the processor. If the arrow is coming out of the processor chip, it means it's an output. So that's kind of the way we define it. We define it from the perspective of the microcontroller, since it is the heart of the system. So the generic system or block diagram for embedded system is you're going to have the inputs, like we said, signal conditioning, whether it's analog, whether it's op-amp or amplifier or something like that, and then data conversion. And many times the data converters are inside the microprocessor or the embedded computer these days. So they've sucked the data conversion inside of it, and then you'll have some output drives like a motor or a display, and then you'll have a motor, typically a motor or something that's high power, actuator, and then up here a user interface, you'll have a display or a keypad, and then you have a hardware linked to other systems. So that's a generic block diagram. And so embedded systems involve lots of different areas: digital electronics, analog, sensors and measurements, electric motors and actuators, control engineering, software, computer, data communications, integrated circuit design. So many different areas of disciplines are involved. And some essential parts of a computer, again, is that a typical computer, a single integrated circuit, is called a microprocessor. So you have a central processing unit, again, inputs and outputs. You have data memory and then program memory. So memory is a huge part of a central processing unit. It has to have a place to store data. So it's not just inputs and outputs on the outside world, but also has to have inputs and outputs for program memory and data that do not really go out to the outside world as far as we're concerned, as far as the human is concerned. But this is an area that the microprocessor needs to do its own processing internally. So this is essential to the computer. So there's two different basic ways. Now we're in section 1.3 of organizing the memory. There's two different types of memory. In section 1.3.3 is volatile and non-volatile. That's on page 10. Talks about those two. Volatile means that it would be memory that goes away when the power goes away. So volatile memory is SRAM or SDRAM. The memory modules that you put a computer to upgrade your memory, those are volatile. Non-volatile would be your key fob on your keychain. That's called flash. Or inside your camera. Or a card that goes inside your camera, so that when you take those pictures, you can take that card out with no power, and then it still remembers it has the data inside of it. So that's volatile and non-volatile. Then we also have two different architectures: the von Neumann way and the Harvard way. And these are named by the people or the university that started them. So von Neumann was a man, and he said that you should have separate data and program memory. Or I'm sorry, you should have the same data and program memory. So you have one address bus, you have one data bus, okay? And so you can share that memory with the same bus. So if you're a central processing unit, you want to talk to program memory, you have to go through the same address bus that your data memory is at, and also your input-output. It makes it very simple architecture for the computer. You only have to have one set of address lines and one set of data lines, but you can only access one block at a time. Now the Harvard way is that you can have separate program memory bus, separate input-output bus, and separate data memory bus. Okay. So this is nice because even though it's more complex, the central processing unit can process memory, program memory, input-outputs, and data memory all at the same time. So it's faster but at the expense of more complex. So most of the microcontrollers are going to be the Harvard way, okay? Whereas your PC, your main PC, or your laptop would be the von Neumann way, okay? So the next section is what can computers actually do, instructions and instruction sets. Well, they can execute instructions in its ALU, arithmetic logic unit. Okay, running a series of instructions called a program. So the ALU can only do a few things, but it can do them very fast. Okay, so it can do things. Arithmetic logic unit means it can perform arithmetic, and it can also perform logic. Arithmetic meaning addition, subtraction, multiplication, division. Logic meaning and, or, nor, not, exclusive or, things like that. So it can do both logical operations, greater than, equal to, less than, and it can do adding and subtracting. So that's a unit inside of the computer. Okay. And these are just some examples of those that you can go through as well. Okay. So the next thing we should talk about here is the RISC architecture and the complex architecture. So there's two different types of architectures. Okay. So the first one we'll talk about is a complex instruction set. So it's a CISC. So the idea with this is that we want computers to execute code as fast as possible. But how to achieve this aim is not always an obvious matter. Okay, so one approach is to build sophisticated CPUs with vast instruction sets, with an instruction set ready for every foreseeable operation. This leads to this complex instruction set computer. This architecture has many instructions and considerable sophistication, yet the complexity of the design needed to achieve this tends to lead to slow operation. That's on page 10 in your book. Okay. So even though you have lots of instructions and they're very complex and they can do instructions, they can do pretty much anything you want them to do instantly in one instruction, well, it causes you to have tons of instructions, and so the hardware, the silicon, the actual chip, has to be big and complicated and expensive. That's like your Pentium processor, okay? But that's not what we're going to be talking about in this class. We're going to be talking about mostly RISC architectures. That's what's used for most embedded systems. And the RISC architecture takes a different approach. The approach is to keep the CPU as simple as possible, to keep it cheap, to keep it small. You want something to be very small inside of your iPad or inside of your well, maybe not iPad. For an iPad, you may want to have a larger processor, but something inside of your refrigerator, something inside of the gas station pump. You know, you don't really need something blazingly fast. You just need to control a basic operation, send some data, things like that. So you want to have a very simple CPU with limited instruction set, and so that's called a reduced instruction set. So the number of instructions that the computer, the instructions are just codes. It's kind of like the codes that the computer understands, and that comes into coding. When you talk about programming the microprocessor, you actually have to write out each instruction that you want the processor to do. So that's an instruction, and that's where you get involved in the software. So in this class, you're going to be doing both the software design. You'll be doing software programming, and then you have the hardware aspect. That's actually physically wiring stuff up on your little boards and things. That we'll do some labs on that. So this leads to the RISC architecture can lead to very fast operation as well. It's characterized by few instructions, say below 100. Each performs a very simple action. So maybe to AND two numbers, or to not two numbers, or maybe to loop if a certain number is higher or lower than that. Very simple, not really complicated. And then all instructions are typically a single word, and all or almost all instructions take the same length of time to execute. Okay. Whereas in the other architecture, The CISC machine is recognized by many instructions, say over 100, maybe 200 or 300. The instruction words can be of different length. Okay, so there are different number of bytes or words inside of there, which you may have to go grab in order to execute the operation, and the instructions can take different lengths of time. So that's it's harder to make that type of a silicon or hardware inside of the chip. So the RISC architecture, which is what we'll be using in this class, is just simpler, cheaper, and that's the point. We want chips that cost 50 cents or $1 or $2. We don't want chips like the Pentium that cost 50 bucks. Okay, because if it's 50 bucks, then that pretty much you can't use it. Because if you're designing something that you're going to sell for 10 bucks, the process it needs to cost you $5, and then if to make 100% profit, that's typically what companies make. If the end product is 10 bucks and the cost needs to be 5 bucks, that means you have packaging, you have all different other types of chips, so your processor needs to be like 50 cents or less. So this is like a real world problem and scenario that leads to this type of an architecture for simple devices. Okay. So that gets us into section 1.4, which is called the microcontroller, and we will talk about that in the next video session. So thank you, and we'll see you for the next session.